Okay, so in this video, we're going to write our first sort of MPI parallel program. In the previous video, I didn't show you the content of test.c, which was a C source file, which sort of printed hello world from different processes, and then it showed like I'm process number 0, and then out of like, I don't know, 4 processes, 10 processes, or whatsoever. So without further ado, let's jump into the first example. Touch main.c. First thing to notice is that you already noticed that we shifted from C++ to C. There are mainly 2 reasons for that. The first one being that we have already a dedicated case, a dedicated sort of, maybe not a course, but a dedicated series of videos to C++. So if you are interested into semantics, syntaxes, features of C++, please go back and watch Learning by Doing C++. And the second reason is that C is also a very beautiful language. It's close to hardware. It's super nice, and you know that MPI sort of libraries usually have bindings for primarily for C and Fortran. I'm going to add this. We are going to go back and forth between C and C++ so that you don't think that, no, with C++, MPI is not going to work and stuff like that. So we're going to test that as well. So let's jump into main.c. We want to write everything from scratch. The first thing we need is, of course, the MPI header files, mpi.h. And then to print some stuff, we need the standard IO. Oops. Our main function is quite simple. It's going to get no arguments. It's going to return 0. So in serial or in sequential programming, all you need to do is basically say printf and then you say hello world. That's all you need to do in sequential programming. I'm going to add a, I don't know, what is it, a backslash in or a slash in. I always mix them up. So we don't forget to put our semicolon. Let's comment this line. So simply we say gcc main.c and we run a.out. You see that sequentially we get this hello world. But the aim of today's video, of course, is to have this in parallel. The parallel version, so we need to set up our MPI environment. We need to allocate the necessary resources for communication and stuff of that nature. There is a method or there is a function for that, and that is MPI init. You see that it depends, it takes 2 arguments. One is int star argc, it's a pointer, and we have char star 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 star, billions of stars argv. So first thing to notice is that we are working with C, so you got to brush up your knowledge on pointers because we're going to work with a lot of them. No matter whether you are working with C++ or C, the bindings are basically working with pointers, so you have no escape basically. Next thing is that it's going to get two arguments, and my main doesn't take any arguments, so I should be okay to pass in 2 nulls right here and get rid of that. But what this one does, as we said, is just initializes your MPI environment, allocates necessary sort of resources for MPI communication and stuff like it does some stuff behind the scenes, let's say. Then after this statement, which is a must, so every parallel program with MPI needs to have this statement to initialize. Then after this statement, you need to think about things concurrently. And by concurrently, I mean that everything that comes here is going to be seen by every separate process, let's say. So process number 0 is going to see this printf statement. Process number 1 is going to see this printf statement. And process number n is also going to see the same printf statement. After you've done your job, then you need to terminate everything. You need to, deallocate the resources that you allocated, and you need to clean up after yourself. And the method for that is MPI finalize. And you must call this one. Also, it makes sure that every sort of process reaches and calls this function before the processes go down here and return and exit. So this is sort of acts like a barrier as well, that every process needs to successfully call this function. So there we go. Now we say MPI CC. We talked about this one. It's a wrapper around your regular C compiler with the proper sort of libraries and you know, the header addresses and everything. So we say main.c and we say MPI run minus NP4, for example, or 3, who cares? And this time we get 3 hello worlds. Okay, but in the previous example, we noticed that we said, hey, hello from this process out of this many processes. So let's go back to our main function. How can we do that? Let's have a rank and let's have a size. So size is going to be sort of the total number of processes. And this is the one that processes actually. So this is the one that I pass in basically with minus NPI 4, 3, 10, 100, whatever. And rank is a unique identifier assigned to each process. So we want to populate these two fields so that we would be able to say hello world from process this out of that many processes. So in order, you know that these two things are not initialized. And this is not a good thing in programming. You have to initialize your variables. But we're going to populate these by calling a method or a function. And that function is called as MPI come and then rank. So you're going to see that it needs a communicator. We're not going to worry about this thing. The only thing you need to know is that MPI provides us with a simple and default MPI communicator. That communicator is called MPI come world, all caps. And then the second thing it needs is an int star rank. So it needs a pointer to rank. So that's why we use this ampersand. That is the sort of address of operator, rank. There we go. We do the same thing for size, a similar sort of function, but with size. And now we have updated these two sort of rank and size. So you see things are passed by reference, not by reference, but we are using pointers. So when we are sending stuff by pointer, it means that if this method is going to update this value, and the updated value is going to be reflected into here. So you might see that, hey, this thing is not initialized, but it is actually by calling this method. This is going to get filled up with the proper information about rank and size. So now we go back here and we say from process %d, of course, out of %d processes. Let's call it like that, and then we should, of course, add rank and size. If I compile this thing, and if I try to run it, you see that now we have the same statement as we had sort of in previous video. Hello from process number 0 out of 3 processes. Another thing to notice is that 0 to 1, we don't have any sort of let's say order in the print statements, and the reason for that is because all these processes are calling printf independently, and there is no guarantee that the operating system will print everything basically in order from 0, 1, and 2. What else can we do? Okay, when I talked about concurrent sort of mindset, so what it means is that we have an integer ranked. Let's say on my machine, this thing is 4 bytes. So when I run this program with 3 processors, it means that 3 times 4, 12 bytes is going to be allocated, because each process number 0, 1, and 2 are going to have its own copy of rank and its own copy of size. So that is what I'm talking about concurrent sort of mindset or thinking, is that every sort of process has its own copy of variables. That is why we call this something as, let me comment this, SPMD. So this is basically single program, multiple data. That is what we are having basically right now. We have multiple data, rank and size right now. And then we have a single program. So every process is gonna basically go from 0 to hero, from the beginning of this main function to the end of this main function. But MPI also supports something which is called as MPMD, which you might have guessed that is multiple program, multiple data. In order to show an example for this one, let me copy main.c into test1.c, and let's go back to test1.c. Here I can say, let's restrict this statement here. I can say if rank equals to 0, so if process number 0 comes and sees this block of code, I want process number 0 to execute this thing. So I'm going to remove that thing, and I'm going to save this thing. So it's going to say hello world from process number 0, of course, out of how many processes? We have no idea. So I'm going to copy test1.c into another program, which is called as test2.c. Let's go to test2.c. And here I'm going to say, for example, process with rank number, I don't know, 4, for example. I wanted to say hello back from process number 4 and out of processes, I don't know how many we're going to have right now. So now we have 2 instances or 2 different programs which are written in MPI, right? So let's just compile them. MPI cc test1.c minus o test1, that's the executable, and MPI cc test2.c minus o test2, and that is the executable. So we said MPMD, that is multiple programs, multiple data. So now we have 2 programs, test1 and test2. Check this out. I can say MPI run minus NP, for example, 3 processors. And then I want to run with test1, and then I'm going to use the colon. Then I'm going to say NP minus NP 5, so 5 more processors, and then test2. So I'm going to run test1 application simultaneously with test2 application. For test1, I want to have 3 processes, and for test2, I want to have 5 processes. If I hit the return key, you're going to see, hey, hello world from process number 0 out of 8 processes. You see 3 plus 5 is 8 in total. And then hello back from process 4 out of 8 processes. So MPI also supports MPMD. So you've learned also about SPMD and MPMD. What else can we say in the first session? Let me also show you that these things are not only magic for C. We can basically copy main.c into main.cpp. And let's jump into, main.cpp. The only thing we need to change is this standard. It should be IO stream and without the .h. And the next thing to change, of course, we don't have printf here. We have std cout, and then we get rid of this one. We say hello world from process. There we go. From process of rank. We don't need that %d anymore. Instead, we say out of. And then again, we close this thing. Size. We don't need that. And then we have processes. And we need to also get rid of everything in the end. And in order to make it more beautiful, I can maybe break it somewhere like here. So that's it. That's the only changes you need to make. So now instead of MPI-CC, you will call MPI-C++. The same thing. It's a wrapper around G++ compiler. Now we say main.cpp. That's going to generate us the basically the executable a.out minus np4, and then you say a.out. If you run it, you're going to get the same result as the .c version. So as I said, everything we say works both for C and C++. And basically today you learned how to work with how to write your your first program in MPI to print hello world from different processes. You got introduced to the notion of SPMD and MPMD, so you can have multiple programs working with multiple data and single programs with multiple data. You learned about MPI init, which initializes the MPI environment, and then you learned about how to populate ranks of each process and also how to populate the total size of the processes. And then you learned about a finalize function, which basically cleans up whatever mess we make after those MPI communications. The next thing I want to draw your attention to is to go back to the sort of standard. As I said, this sort of a standard. Try to download this. This is super important. We're gonna go back and forth between the standard and the code a lot of times. So let's read the introduction part of chapter 1. It says MPI is a message passing library interface, a specification, and all parts of this definition are significant. So everything which is written in italics. So basically it is message passing library interface, a specification. It's not a representation or it's not an implementation, but it's just a specification. So MPI addresses primarily the message passing parallel programming model. It's not the only parallel programming model, but it is the one that we are working with right now. And the meaning for that is that the data are moved from the address space of one process to another process through cooperative operations on each process. This thing is not important, then this one is important. MPI is a specification, not an implementation. There are multiple implementations of MPI. We talked about OpenMPI, MPeach, Intel one, IBM one, whatever. This specification is for a library interface. MPI is not a language, it's just a library. And all MPI operations are expressed as functions, subroutines, or methods according to appropriate language bindings that for C and Fortran are part of the MPI standard. There we go. I think those were sort of the important statements in the introduction. The main advantage is that we have portability and ease of use in distributed memory communication environments, you know. And another thing which is important is that I talked about MPI init, but you can also initialize your MPI environment with something which is called MPI init thread. So this means that MPI library intrinsically doesn't prevent you from multi-threading. So if you know how to also program with OpenMP, how to parallelize with OpenMP, so MPI is not basically, you know, cutting your hands basically to do that. So you can still do multi-threading. If you want to do multi-threading, you need to initialize your environment with MPI init thread, and you need to also make sure that the implementation of the MPI library, in our case is OpenMPI, is actually sort of, let's say, OpenMP compliant, or it is compatible with OpenMP as well. So there are also checks that you can check that whether you have this, but OpenMPI does also support multi-threading. There we go, I think. And then you have a bunch of backgrounds here, which are probably not interesting to us. And the next thing, which was probably important, I marked it here, is that what platforms are targets for implementation. The attractiveness of message passing paradigm at least partially stems from its wide portability. And programs expressed this way may run on distributed memory multi-process networks on workstations and combinations of all of these. So you can have also, as I said, shared memory implementations on multi-core processes as well, on hybrid architectures or whatever. So MPI is not basically cutting your hands to do other means of parallelization. The interface is suitable for use by fully general. This is what we said, MIMD, so multiple instruction. This is the generalized version of MPMD. So we have multiple instruction, multiple data programs, as well as those written in more restricted style of SPMD, which is the single program, multiple data. There we go. I think these were sort of the most important things that you needed to know. And MPI provides many features intended to improve performance on scalable parallel computers with specialized interprocessor communication hardware. If you're interested, you can go read the rest of it, and you're going to see that what is included in the standard, these are all the things that you can learn from the standard. So you're going to learn about point-to-point communication, partition communication, data types, collective operations, all the way to down here. Then this section, I very much actually like this 1.14 section, which is the organization of this document. It basically summarizes each chapter, what you're going to learn about each chapter. I do encourage you to read these things. I don't want to spend time on this. I think already this video is basically too much for today. I hope you learned something from this video and hope to see you in the next one.